Hello, I'm back. Sorry I haven't posted in the last 2 days. I've been sick, but now I'm no longer sick. Today, we are doing the art of geometry. Exciting. This is a bunch of squares that I have made. Yes, they're all squares. If you want to look at them, do that. I challenge you to find out that they're not squares. Okay, first up, we have the Steinhaus notations. Before we continue back on our endless hunt for numbers, which was all the way back here in tree 3 and the googolo and plexica numbers, I want to talk about a different notation. You don't have to, but I want to, and you're watching it, so you really have no choice now, do you? Okay. So, much like Graham's number and the Graham function and the tree function, uh, the Steinhaus notations are geometric. They don't have anything to do with geometry, but they are notated as geometric symbols. The circle, just so you guys know, will be replaced with the pentagon for reasons that I will explain later. So, the Steinhaus-Moser notation, three shapes are used: the triangle, square, and circle slash pentagon. It'll be the pentagon here. So, most of the stuff that we'll be talking about will be in pentagons, but I just want you guys to know the full story. This one's going to be a bit short, by the way, because I'm sick and I made this in the past like an hour. So, the Steinhaus notations, I'm going to refer to them as Steinhaus notations, as there is a different thing that is named Moser in here, and I don't want confusion. Triangle, which is the triangle of n, is equal to n to the nth. So the triangle of 2 is 4, the triangle of 3 is 27, so on and so forth. The square of n, which can be confused to the second power, is that encased in n triangles. So the square of 2 is 2 encased in 2 triangles. So it's 2 and then 2 up arrows and then another 2, which means 2 to the 2 to the 2, which means 16, I believe. And then 3 is a lot bigger, and I don't really want to get into it. So, and then the pentagon, which I know it's a bit oversized. Once again, I'm very tired, and I made this in the past hour. It's n encased in n squares. So the pentagon of 2 would be 2 squares, which would be 4 triangles. So 2 to the 2 to the 2 to the 2 to the 2. That's wrong. Okay. The pentagon. Okay. So n encased in polygon with n sides is equal to n encased in n amounts of polygons of a side less than the original polygon. So this is a polygon, obviously. All these are polygons. So this has 5 sides, 4 sides, 3 sides. There's no 2-sided polygon. There's no 1-sided polygon, at least not on a 2-dimensional plane. So the triangle is the lowest that you can get. So, this is a very slow function compared to, say, the Graham function. The Graham function, any of the Conway functions, the tree function, obviously, the googolo and plexica functions. So yes, but it is very fast. The pentagon of 2 is 256, followed by 256 up arrows, followed by another 256. That's the mega. A megastin is the pentagon of 10, which is 10 quadrated to the 11, or 10 quadrated to the 12. It's in between those two. Yeah, so this is how Steinhaus notation works. Moser's number. Yeah, so obviously Professor Google needs his big numbers. Today's is Moser's number. Moser's number is taken by it is the megagon of 2. So what a megagon is a polygon with this amount of sides. So this is an extremely large number, And now, so 2 encased in that side amount of, in a polygon of that amount of sides, which is keeps on going down and down and down until you have the triangles, which is an obscenely high amount of triangles. It's, however, it is nowhere near Graham's number or tree 3, any of the trees or any other functions that we've encountered so far. So why do we care? The Steinhaus notation is important because there's no limit on what can be used. G64 instead of a G64 would be far surpassing tree 3. Not tree 4, though. I believe tree 4 would much surpass this. Tree 3 instead of tree 3 is tree 3, followed by tree 3 up arrows, followed by another tree 3. So yeah, it's, if I'm doing my math correctly. So it's fast and it's convenient. We don't have to draw anything. And eventually, even if we did have to draw stuff, it'd just be a circle with the amount of sides. So now we're going to do Google number line because I wanted to extend the video past the 6 minutes it's been. So the first is the Google. The Google is the smallest official googologic number. It's the flagship of googology, hence the name. One followed by 100 zeros. I would have written it down here if I were not lazy and didn't want to. Second, Googleplex. It's 1 followed by a Google zeros. It is not able to be written out in the entirety of the observable universe. It has about 20 more zeros than the amount of atoms in the universe. So yeah, it's nowhere near being able to be written out already. But with notation, it's very easy to write out. It's just 1. It's 10 to the 10th to the 10th. Third is the mega or the megastin. Both of them, I decided to put them on the same slide. Pentagon of 2 and 10, 2 and 10 respectively. It is some of the smallest of the highest Steinhaus numbers. And by the Steinhaus numbers, I mean the numbers that are created by Steinhaus notation, especially pentagons, because squares and triangles are almost never used. Moser's number is the 4th. It is the megagon of 2. It is one of the largest in reasonable Steinhaus. It is extremely large to the point where I cannot describe how large it is, but obviously. 5th is Graham's number, which you've all heard of, the upper bound of a problem in Ramsey theory, represented as G64, the Graham function. The Graham function does not actually exist. I made that up, but it does make sense that it would be a function. It's much larger than any of these numbers. 6th, tree 3, the third product of the tree function, far dwarfing even the mightiest of the Graham function. So far, the largest rational number encountered on these slides. It is, yeah, it's extremely large and extremely powerful, the tree function. The tree function stands for something, I believe. I don't really know what it is, though. So, yeah. 7th is Googlo 1. The Googlo 1 is the largest number that can be created with one non-recursive operation. There are no functions allowed. This is a function that I've created by myself. Plexico 1 is the largest number that can be created with one non-recursive function. It's basically just mimicking the strongest function that exists. And not, this says 9th. Don't believe anything that anyone else tells you. So, this is omega. Obviously, lower omega is the smallest infinity. It is at the end of the hypothetical number line, which does not exist. So technically, it does not exist as a number. It is qualitative, as I say here. But yeah, So that's our highest number. Tomorrow, I'll be back with stuff that actually satisfies your needs for googology. But today, I'm just too tired to do anything more than this. So that's Professor Google's lesson today. Hope you guys are happy with that. It's only been 10 minutes, but better 10 minutes than 0 minutes. And you guys aren't getting anything else from me. So, bye. Professor Google is out. Force. after I show off my extremely large amount of squares. Do you know how long this took me? This took me like actually only like 5 minutes. It wasn't actually that hard because I just merged them constantly. But look, creates this nice little circle, and this is totally off center. Why is it off center? God damn it. Gosh darn it. Uh, yeah, so that's it. Bye.